I want to return to the patient suffering from severe chronic back pain. Let's assume over time it was established that when a 40 milligram dose of medicine is given to a patient with a high level of pain, 30 minutes later, the mean pain level is down to 50 with a standard deviation of 5. Suppose we randomly selected 16 such patients and gave them each a 40 milligram dose of medicine. Our understanding of sampling distributions of means determines that sample mean pain levels would be normally distributed with a mean of 50 and a standard deviation of 1.25. So what is hypothesis testing and inferential statistics? If we have an established sampling distribution for this particular medicine, then we could perform an experiment and randomly assign 16 patients to this medicine and 16 to a new medicine. Thank you. Anyway, suppose the mean pain level of the new medicine was down at 45. This is 4 standard deviations below the true mean of the old medicine. We would conclude that the new is better than the old at lowering pain. We know the old medicine works, it just looks like the new medicine works better. With all this in mind, what if we randomly assign 16 other patients to a placebo? That sample mean might be way up here, nowhere near as effective as the old medicine. But not always are results so definitive. What if another new medicine was assigned to 16 patients and the sample mean was 48.9? Yes, the sample mean is less than 50, but it may just be due to random chance fluctuation. In fact, suppose a recently hired analyst, let's just call him the new guy, figured out that the other new medicine wasn't new at all. Someone duplicated the old formula and packaged it under a new name. They just got lucky with the sample mean being below 50, and it tempted people to believe it was actually better than the old medicine, when in fact it was the old medicine. When we analyze sample results, we use hypothesis testing. It assumes a new medicine is no better than the old medicine, and its sampling distribution of means will be exactly the same as the old medicine with the same random chance fluctuation. Knowing that these are the kinds of sample means expected if the new medicine is no more effective than the old, we take one real-life sample and see how it behaves. If that one actual sample mean is way down here, it's behaving like the new medicine is better. If the sample mean of new medicine is 49.2, the difference between it and 50 may easily just be due to random chance fluctuation. Its behavior does not convince us of its effectiveness. If, on the other hand, the one actual sample mean was 47.7, it is still possible to be due to random chance, but is it unusual enough to signify the new medicine is better? Hypothesis testing answers this question using conditional probability, a p-value. If the mean pain level of the new medicine is still 50 like the old medicine, how often due to random chance would we expect to get a result at least as extreme as the sample mean we just got? 47.7 would only be reached by 3%, 0.03 of samples. This means we would only get such an extreme result in 3 of every 100 samples. It's unusually low, and we will conclude with confidence that the new medicine is better. Now, we're not certain, but the odds are in our favor. Typically, any p-value below 0.05 suggests an unusual enough result that we abandon the notion that the new treatment is no better than the old treatment. 0.05 is 1/20th. When we get a result that should only be reached in 1 of 20 samples due to random chance, we assume that random chance is not the explanation for the extreme result. We assume the explanation is a population mean of the new medicine somewhere below 50, perhaps in this case 47 or 48, where such a sample mean of 47.7 is more likely to occur. In other words, the evidence suggests less pain on average with the new medicine.